Today we are going to talk about vertical asymptotes, holes, and horizontal asymptotes. So we've been talking this unit about restrictions. Those are values that cause us to divide by 0. But what we've never talked about officially is what happens when there is a restriction. So vertical asymptotes are what occur in the spaces made by restrictions. So let's look at this first example. We've got x minus 3 in the denominator, and that lets us know that we have a restriction at positive 3. That means that we know that x cannot equal positive 3. So what's happening when we look at positive 3 on the graph? If we look at the graph of this, at positive 3, we can see that there is an imaginary line called our asymptote. Remember, our asymptote is the name of those guidelines we use. So even though that's a restricted value, we can also say that there is a vertical asymptote there, that there is a guideline there. So if we go back to our notes, we can say there is a restriction at 3 because what's happening there is a vertical asymptote at x equals 3. For the next problem, there's 2 asymptotes. There will be a vertical asymptote at x equals 5 and another one at x equals negative 9. Those values don't have anything when you graph them because there's guidelines there. So what we're saying today is at those restrictions, there are guidelines, and we call those guidelines vertical asymptotes. For this last one, we have a little bit of factoring to do. We'll have x plus 5 on top, and then on the bottom, there's that difference of squares. That's that a squared minus b squared format. So we can factor this into x plus 3, x minus 3. And that means that we will have vertical asymptotes at x equals negative 3 and at x equals positive 3. And again, as we look at the graph, we can see at those breaks are those imaginary lines that we just wrote the equations of. So we're writing the equations of those imaginary guidelines, one at negative 3 and then one over here at positive 3. But sometimes something weird can happen. We also get something called holes. We get holes in our graph. And holes occur when factors cancel. And I just want to note that any leftover denominators are still vertical asymptotes. So let's take a look at this first example. You'll notice that these factors cancel. We can say goodbye to both of these. So that restriction happens at negative 4, and that means that there's going to be a hole at x equals negative 4. So let's look at our graph to see what happens. So here's our graph. We can see that there is an asymptote at 2, and that makes sense because we have x minus 2 over here. But negative 4, it doesn't look like anything's happening there. But if we take a closer look and we drag our mouse and we line up right on negative 4, which is sometimes hard to do, you can see that it's undefined. And if you look right where the mouse pointer is, you can see that that's an open circle. There's a hole in the graph. It's hard to see on Desmos because if I let go of my mouse, it goes away. So you have to know where to look for it. And the only way to do that is by finding the factors that cancel. So here we have a hole in the graph. You can see the dot changes because there is an super teeny tiny gap in our graph at negative 4. So holes occur where things cancel, and then of course we still have that vertical asymptote at positive 2. So we'll go back and write that. We've got a hole at negative 4, and then we still have that vertical asymptote at x equals 2. Sorry, I don't know where that line came from. X equals 2. There we go. Okay, so this next one. When things cancel, that means there's a hole there. So we will have a hole at x equals 7. And then anything left over, we still have a vertical asymptote. So we'll have a vertical asymptote at x equals negative 4. And if we look at the graph of this, we can see, yep, there's that imaginary guideline at negative 4. But also, if we click on 7, there's that hole. It says undefined there because there's a little teeny tiny hole in our graph. This third one is a bit of a challenge because you have to factor the numerator. So let's factor the numerator. We got to think of two numbers that add to 1 and multiply to negative 20. So x plus 5 and x minus 4. And then on the bottom, that's already factored, x minus 6, x plus 5, x minus 4. So this graph is going to have two holes. It's going to have a hole at negative 5. And it's also going to have a hole at positive 4. And then still that leftover denominator means we're going to have a vertical asymptote at 6. So we can look at our graph and check our work. We expect a hole at negative 5, a hole at positive 4, and then a guideline at positive 6. So here's our graph. We can definitely see there's the guideline at positive 6. And then if we look at negative 5, there's our hole. I almost had it. There it is. And then there's also going to be one at positive 4. Oh, right on it, first time. So that's why you can't just use Desmos to find the holes, because if you look at the graph right now, you wouldn't know that there's holes at negative 5 and 4 unless you know exactly where to click. And you know where to click because you did this algebraically in your notes. So vertical asymptotes are those up and down guidelines, and holes occur when factors cancel. And if there's leftovers, those are still vertical asymptotes. But now we need to talk about those other guidelines, those horizontal asymptotes. To find horizontal asymptotes, we focus on the degree of the numerator and the denominator. You're already in the habit of focusing on those degrees because we did this when we found improper and proper fractions. So this picture looks ridiculous, but this is a dude named Bobo Botten. And as you can see, he is feasting on DC. So this is a silly little mnemonic device that will help you remember how to find horizontal asymptotes using the degree of the numerator and the denominator. And here is how this little device works. Bobo stands for bigger on the bottom. The horizontal asymptote is going to be y equals 0. Botten stands for bigger on the top. There is going to be no horizontal asymptote. And then finally, if the exponents, and remember, that's just a different way to say degree. Degree comes from exponents. But DATS DC doesn't make as much sense as EATS DC, which still doesn't make any sense, but hopefully it's a little easier to remember. If the exponents are the same, then you will divide the coefficients. And if you're asking, what in the world does that mean? Don't worry, I've got you. I'll show you what I mean. So let's look at these next 4 examples. We're going to use their degrees, and we're going to use this little mnemonic device to help us think about where the horizontal asymptotes are going to be. So this first example, let's look at the degrees. We've got a degree of 2 and a degree of 3. So that is bigger on the bottom. So this is a bobo. It's bigger on the bottom, and that means that the horizontal asymptote is at y equals 0. So here the proof is in our graph. We can clearly see that there is a horizontal line at a height of 0. Let's look at this next one. Here we have a degree of 4. Here we have a degree of 3. So this is bigger on the top. So we say bottom. If it's bigger on the top, then none. There is no horizontal asymptote. So what does that look like? Let's take a look. So looking at this graph, you can see that there's not a horizontal guideline. There's actually what we call a slant asymptote because you can see a diagonal guideline, but we're not going to worry about that in Math 3. I also don't want you panicking because you aren't going to ever have to graph this in this course, but you will need to determine that there's no horizontal asymptote. So if you can recognize, hey, the degree is bigger on top, there's no horizontal asymptote, that's all I need from you. So for this next example, let's look at the degrees. We've got a 3 and a 3. So those degrees are the same. Those exponents are the same. So when that happens, we divide the coefficients. Coefficient is the fancy math word for the numbers out in front. So we're going to divide the numbers out in front, which is 8 divided by 2. That means our horizontal asymptote is going to be, here, let me label this real quick. Our horizontal asymptote is going to be y equals 8 divided by 2, which is 4. And we can show that in our graph as well. We can clearly see that there is a horizontal guideline with a height of 4 on our graph. Let's do one more like this. Here we've got an exponent of 2 and an exponent of 2. So those exponents are the same. So this is another case of when the exponents are the same, we will divide the coefficients. If there's not a number out in front, remember you can always assume there's a 1 there. So when we divide these coefficients, it's going to be 1 over 4, which is 1/4. So y equals 1 over 4. All right. Let's find all three, vertical asymptotes, holes, and horizontal asymptotes for these two examples. But before we do, I want to make sure that you are very clear on the fact that when you find vertical asymptotes, you always use an equation for x equals, because x equals always gives you a vertical line. When you do horizontal asymptotes, you always use y equals, because y equals always gives you a horizontal line. And for holes, you just say where they are on the x-axis. Okay, so let's look at this first example. In order to get it done, we first need to factor. So let's factor the denominator, and the numerator. Our numerator has a GCF of 3, so we're going to have a 3 up top and then x minus 1. On the bottom, we're going to do x and a blank, and we need two numbers that add to 3 and multiply to -4. So -1 and +4. First thing we want to do is actually look for our holes, because those are things that we can cross out. So we are going to have a hole here at +1. So hole at x equals 1. Next, we're going to find our vertical asymptote by looking at our leftover denominator. So here, our leftover denominator is x plus 4, so we're going to have a vertical asymptote at x equals -4. Finally, we're going to use the degree of the numerator and the denominator to help us find the horizontal asymptote. So let's look at our degrees. The degree of the numerator, there's an imaginary 1 right there. The degree of the denominator is 2, so that is bigger on the bottom. So this is a bobo situation, and bigger on bottom means that y is equal to 0, so that is our horizontal asymptote. So we found all the characteristics, and as always, a great way to check your work is to graph it and see if those answers make sense. So let's see if we've got it. Do we have a hole at 1? Yes, we do. I just saw it. Yep, there, we have a hole at 1. Do we have a vertical asymptote at -4? Yes, we do. There is an up and down line at -4. And do we have a horizontal asymptote at 0? Yes, we do. There is a horizontal line with a height of 0. All right, last one. First, we got to get our factor on. So x plus 3, x minus 2 over x minus 2, x plus 1. All right, let's find our wholes first. That's the easiest thing to look for because it's based on what cancels. So we are going to have a whole at x equals 2. Now what's left over in the denominator is x plus 1, so we will have a vertical asymptote at x equals -1. And then finally, we're going to use our degrees to figure out our horizontal asymptotes. So 2 over 2, which means we divide the leading coefficients. Remember, if there's no numbers out in front, you can assume it's 1 over 1, which is just 1. So our horizontal asymptote is going to be y equals 1. And again, you can check your work with Desmos, which I always encourage you to do. So do we have a whole at +2? Yep, there it is. Do we have a vertical asymptote at -1? Yes, we do. And do we have a horizontal asymptote at +1? Yes, we do. So those are the big takeaways from today. We find vertical asymptotes based on where the restrictions are. We find wholes based on where we cancel factors, and then we use the degree of the numerator and the denominator, and then we use this silly little mnemonic device to help us figure out where our horizontal asymptotes are. Can you use Desmos as a guide? Yes. The only caveat is that you can't use Desmos to find wholes. You have to be able to find them by hand, because if you don't know to click right here at +2 to find a hole in the graph, you're never going to see it. So it's important. I can't do it either, apparently. Come on. I almost had it. There it is. So it's very important to know how to do this algebraically and not just by plugging the function into Desmos. All right. Thank you for listening.